Good morning. So, yeah, my name is Vlad Khononov. My last name, you can pronounce it however you want. It doesn't really matter anymore at this point. So, usually I wear two hats. The first one is senior cloud architect at a company called Do It International. The second one is I am doing consulting. I specialize in distributed systems and, of course, domain-driven design. Speaking of which, who got this book except the balls? You are awesome. Wow, so many hands. And keep your hands up if you liked it. Wow, people, you are awesome. Wait a second. That deserves a selfie. Let's do a selfie. OK, cool. So speaking of books, you know, there are two books that really changed the way I think about software design. Now, try to guess what's the first one. Not really. Yeah, the book that started it all. Domain-driven design by Eric Evans. The second one, however, it is much less obvious. And it's not obvious because it has nothing to do with software design. In fact, it barely mentions the notion of software at all. It's a book about physics, biology, social sciences, and most importantly, complex adaptive systems. The book is called Scale: The Universal Laws of Growth, Innovation, Sustainability, and Pace of Life in Organisms, Cities, Economies, and Companies. The author, Professor Jeffrey West, starts the book by sharing some peculiar observations. He says, let's take a few quantities that play important roles in our lives, such as how much food do we need, how creative are we, how profitable are our companies, and plot these quantities against the sizes of relevant systems. For animals ranging from mice to elephants, their metabolic rate, or in other words, how much food they need to stay alive, results in an almost straight line when plotted against the animal's body mass. If we use the number of registered patents as a model for measuring creativity of people living in different cities, then again, the number of patents results in an almost perfect straight line as a function of the city size, its population. And finally, plotting the assets and incomes of publicly traded companies against the number of their employees, again, it organizes the measurements in approximately straight lines. Now, what is going on here? These systems are what we call complex adaptive systems. By definition, they're producing emergent outcomes that are difficult and even impossible to predict simply by looking at the individual components of a system. Yet, here we are. If we look at each of these systems as a collection of individual cells, citizens, or employees, the emergent behaviors are lining up in almost perfect straight lines. And again, the common denominator in all these charts is the horizontal axis, the size of a system, meaning that important attributes of complex adaptive systems can be predicted just by knowing their size. For example, knowing the body mass of an animal gives us much more information than really depicted here. It also reveals the animal's average heart rate, its pace of life, risk of getting tumor, lifespan, and many more. And same is true for other complex adaptive systems like cities, companies, social networks, traffic flows, and others. And this was the goal of Professor West's research. He wanted to use the observations on how systems respond to change in size and use it to uncover some shared governing principles that underline all of these very different and highly complex phenomena. As he put it, viewed through this lens of scale, cities, companies, plants, animals, our bodies, and even tumors manifest a remarkable similarity in the ways that they are organized and function. Now, at this point, I think you may be asking, well, this is definitely interesting, but what it has to do with us? Like, next week, I get back to work. How this graph about animals' metabolic rate is going to help me to do a better job. And the thing is, although the book doesn't even mention the notion of software design, boy, all this stuff has so much to do with our work. These universal laws of growth, innovation, and sustainability mentioned in the title apply not only to organisms, cities, economies, and companies, but in general to the kind of systems that Geoffrey West describes as energy supply networks. As we're going to see a bit later, software design is one of such systems. So this is our agenda for the next 45-ish minutes. We'll start by exploring what are these energy supply networks and what makes them so special. Next, we'll see how this theory applies to software design, and ultimately how we can leverage it to manage the complexity of, of software systems. Overall, you will see that the same laws of physics that govern the growth of business and cities, they are the same laws that restrict growth of software systems. In the process, we are going to consult Galileo Galilei on why a code base degrades into a big ball of mud, and discover how this little acronym here, S-D, can tell you almost everything you need to know about a software design decision. So, what are these energy supply networks? Stated simply, energy supply networks are systems that are sustained by the transport of energy through hierarchical networks. In one way or another, the energy is extracted from the system's environment, and it's delivered across the system. In such systems, they are everywhere. Almost all aspects of our lives are controlled by energy supply networks. And the simplest example is you are. You are an energy supply network. The air you breathe, the water and food you consume are transformed into the energy that powers your body. And we are just as other mammals, animals, plants, and all living organisms. They are all energy supply networks. A typical example of a human-made energy supply network is a city. A city provides water, electricity, communication, transportation, and other infrastructural services to its citizens. As living organisms, a city supplies energy. Now, organisms and cities, these are examples of physical networks. But energy supply networks can also be more conceptual or virtual. For example, a company has to deliver energy in form of wages to its employees. It also controls flow of information across the company, connecting multiple sources such as employees, department managers, and the CEO. The flow of this information powers the company. Another human-made energy supply network is the internet. Here, the energy is the data, the information that is shared across the network. All these examples are what we call complex adaptive systems. They are composed of enormous numbers of elements, and the behavior of the overall system results from the interactions of all of its components. And again, we cannot predict how the system is going to behave by inspecting an individual component. That said, according to Geoffrey West's research, all energy supply networks are controlled by the same physical laws. So if we could define software design as an energy supply network, we could leverage that knowledge from other fields to make smarter software design decisions. So let's do it. Let's see what makes software design an energy supply network. And the main question we have to answer here is, what is the energy that is supplied by software design? What do you think? Information. Close. Data. Close as well. We'll discuss it later. Other ideas?
User value.
Value. Close as well. What about don't repeat yourself principle? There is an explanation saying it's not about code, but it's about knowledge. Yes. Knowledge. So when we build software, we design elements such as bounded context, services, components, modules, classes, or individual methods. And what's common to all of them is that they all have a boundary that encapsulates some of the knowledge inside of that component and let some of the knowledge to flow across the boundary through the public interfaces. The way two modules are integrated, or the amount of knowledge that is shared across their boundaries, it has a profound effect on the design of a system. The more knowledge is shared, the more often the modules are going to have to change together. And we can roughly categorize the knowledge that can be shared across boundaries into 4 types: implementational, functional, model, and contract coupling. As the name suggests, implementation coupling is about knowing the implementation details of another module and using them for integration purposes. In other words, a module ignores another one's public interface and just uses some private interfaces for integration. A typical example is, let's say we have 2 classes, and one of them uses reflection to access a private field of another class. Well, that was never intended for integration. So that's implementation coupling. Needless to say that such integration method is fragile and implicit. The authors of that second module class, they may not even be aware of the integration taking place. And thus, every change they're making in the implementation details, it has the potential to break the integration. So we have to assume that all knowledge about how the module is implemented is shared. Next, functional coupling means that the connected modules are sharing the knowledge of the business functionality they're implementing. Its practical implication is that the same business requirements are going to trigger simultaneous changes in both components. The extreme example of functional coupling would be 2 modules implementing exactly the same business logic. When the requirements change, the modules will have to change together. Furthermore, functionally coupled modules don't have to be connected physically. Even if that duplicated logic is implemented in unrelated, unconnected parts of the system, they are still going to have to change together. They are still sharing that knowledge. A lower level of integration strength is model coupling, meaning that components are using the same model of the underlying business domain. Here again, when the model changes, the changes will have to be propagated across the boundaries of these components. And finally, the lowest level of shared knowledge is contract coupling. Here, the components are integrated through an explicit integration-specific model that is decoupled from their implementation details, meaning that implementation, it can evolve independently of the integration contract, thus minimizing the cascading changes and minimizing the shared knowledge. A typical example of contract coupling in domain-driven design lingo would be using a published language. It's an integration-oriented model that doesn't reflect any knowledge about how the second module is implemented, its functional requirements, and the models that module uses internally. As Ruth Malan famously said, system design is inherently about boundaries. Boundaries define how knowledge is flowing through a system and what kind of knowledge is shared between the different components. Now, going back to my previous question about what is the energy, 2 of the answers were data and information. So now we can compare them. Imagine sharing like petabytes of data through a contract-coupled interface. It's going to expose way less knowledge than sharing a few bytes of data through an implementation-coupled interfaces. That's why software design pumps knowledge through the system. That's the energy we're dealing with here. So now we can say that software design is an energy supply network. Software systems are sustained by the transport of knowledge through hierarchical networks of modules. Module component boundaries are the pipes through which the energy of knowledge is pumped across the system. And now we can leverage this insight on how energy supply networks work, how they scale, and use that to design better software. And let's start by talking about how energy supply networks grow. So organisms, cities, companies, and overall all energy supply networks all tend to grow over time. Let's see what makes growth so special, what makes it so attractive. So in the beginning of the presentation, you saw these three graphs showing that different attributes of complex adaptive systems can be quite predictable and reveal some useful insights about how systems react to changes in size. However, I purposefully omitted an important detail. These resulting straight lines make it easy to assume a linear dependency between the quantities. For example, in the case of metabolic rate, it's easy to assume that a change in the size of an animal will result in a proportional change in its metabolic rate. That's not the case. If you look closely, you will see that these graphs are logarithmic, meaning that the values on the both horizontal and vertical axes increase by factors of 10. If we were to plot this data linearly, we would get elephants right there in the middle, and the rest of the animals crowded right there in the left corner. Logarithmic scale allows us charting wider ranges of data on a more compact area. However, if we focus on the chart on the right, the linear one, it shows an interesting behavior. The metabolic rate grows as the 3/4 power of body mass, meaning that the metabolic rate grows sublinearly, slower than any possible linear function. Is this insight useful for us? Of course it is. Let's see an example. Say we have these 6 dogs of different sizes, from Chihuahua to Newfoundland. As you can see, I picked the dogs so that the average body mass is doubled. Chihuahua weighs about 1.8 kilograms. Yorkshire Terrier is twice as big, 3.5, Pug is 7. All the way to Newfoundland, that can weigh 58 kilograms. Now, let's say we want to know what is the basal metabolic rate of these dogs. What is the minimum number of calories a day they need to stay alive to support their basic life functions? So no playing, no running, just chilling, relaxing all day long in a comfortable temperature. How many calories they need for that? And for Chihuahua, it's 110 calories a day. Yorkshire Terrier is twice as big, so it probably needs twice as many calories to feed its twice as many cells. So it will be 220. Again, twice as much for a pug, beagle, boxer, until we get to the biggest one that needs whopping 3,500 calories a day. This linear thinking sounds logical, it sounds reasonable, it sounds rational, it's easy to understand, but it's wrong. It's wrong because metabolic rate grows sublinearly, meaning that for every doubling of size, the metabolic rate increases only by 75%. As the organism becomes bigger, it becomes more efficient. It is especially evident here in the example of the biggest one, of the Newfoundland. It requires less than half of the energy one would assume it needs by following into the linear thinking trap. So, of course, the sublinear growth dynamic, it is not unique to dogs, and it's not unique to organisms, but you can find it in every energy delivery network. For example, here are the results of a study that evaluated how many gas stations are needed in cities of different sizes. This one describes what happens here in the Netherlands, but the dynamics are exactly the same all over the world. Furthermore, it is true for all infrastructural networks of a city. For every doubling of its size, it requires only around 85% more roads, electrical wires, water pipes, etc. Now, let's look at a similar, but at the same time, very different growth dynamic. For that, let's examine the graph of registered patterns in cities of different sizes. Here again, it's easy to assume linear behavior. And again, we have logarithmic scale on both axes. And again, if we plot the same data linearly, we will see a non-linear behavior. Here, the number of pattern scales as the 1.15 power of the city population, meaning that the number of registered patents scales superlinearly, faster than any linear function. The explanation behind this phenomenon is that larger cities enable more possible interactions, more diverse ideas to be shared, and all that results in higher creativity of its citizens. So again, if we take a city double its size, we should expect the number of registered patents to grow not by 100%, that would be linear thinking, but 115%. So these are the economies of scale. As systems grow, linear growth is very, very rare. The vast majority of system attributes grow either superlinearly or sublinearly. And it happens because the system leverages the efficiency of a larger system. How that happens? Spoiler alert, we are going to discuss it later. Second spoiler alert, yeah, it has something to do with fractals. So going back to this notion of representing software design as an energy supply network, we can say that the larger the system gets, the less knowledge has to be added to implement additional functionality. You can build up on the existing infrastructure, existing models, and you can reuse existing functionalities. And speaking in the language of growth dynamics, while the system functionality grows linearly, the added knowledge grows sublinearly. Now, this notion of growth-driven efficiency bonus sounds awesome. But it begs the question, well, if growth is so beneficial, then why don't energy supply networks grow indefinitely? Like, if Newfoundland is so much more efficient than Chihuahua, then why don't we have dogs or other animals reaching the sizes of dinosaurs or even bigger? Well, this question, it was answered all the way back in 1638 by Galileo Galilei. He said, you can plainly see the impossibility of increasing the size of structures to vast dimensions, either in art or in nature. Also, it would be impossible to build up the bony structures of men, horses, or other animals so as to hold together and perform their normal functions. For if his height be increased inordinately, he will fall and be crushed under his own weight. To illustrate this idea, Galileo proposes to think about a plank of wood. If we scale it to twice its size, its weight is going to be increased in 3 dimensions. It will be twice as wide, twice as tall, and twice as long. Overall, the weight will be increased 8 times. However, the plank's resistance to fracture, it is defined by its cross-sectional area, which increases in only 2 dimensions, width and height. So we try to do the same with a human. Let's say we take a human and try to double this person's size. Well, the person's weight is going to be increased 8-fold, while the limb's resistance to fracture only 4-fold, meaning that beyond a certain maximum height, the person's joints won't be able to support the stress, and they will break under their own weight. And that maximum height is our actual growth limit, by the way. So all these giants from movies are physically impossible. As Galileo said, all of them, they would fall and be crushed under their own weight. The different rates of growth is the reason why systems cannot grow indefinitely. When stress-inducing factors grow faster than stress-withstanding attributes of the system, that relationship limits the system's growth potential. In more general terms, we can say that when a system grows, yeah, it becomes more efficient. However, some of the undesired attributes of a system, they are too becoming way more efficient. So for example, in organisms, they stop growing again when their limbs are not able to support their weight, or the total number of cells surpasses the organism's ability to supply energy. As cities grow, overcrowding, crime rates, pollution, spread of diseases, all these grow superlinearly, making the city less and less attractive for new citizens. When companies are growing, the sales, incomes, profits, they all tend to grow sublinearly, resulting in the company being unable to support the linear growth in the number of its employees. Also, bureaucracy and management complexity, they are becoming more efficient. And that results in the company becoming slower and slower. And finally, what about software systems? Well, that deserves a whole section. So earlier we saw that when the functionality of a system is expanded, the knowledge that needs to be added to the system, it grows sublinearly, right? Let's see this in action. So let's say we have this system here, and we are implementing some basic functionality. And then we extend it a bit and add another feature, another one. One more, and last one. Have you noticed what was going on here? As expected, we had to add, as we added more and more functionalities to the system, we needed to add fewer modules. We needed to add relatively less knowledge. However, all these lines describing the possible interactions between the modules, they were growing superlinearly. Let's see this again. As explained by Galileo, different parts of the system scale at different rates. The knowledge we add, it grows sublinearly. However, the complexity resulting from the possible interactions between the modules, this one grows superlinearly. So let's add this resulting complexity to our graph. And right now we have three different growth dynamics here. Linear growth for functionality, sublinear for knowledge, and superlinear for complexity. Now, there is one final attribute we have to discuss here, and this is this brown horizontal line. Does anybody want to share any ideas what this is? Sorry? I cannot hear you. Yes, 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 yes. This is our cognitive limit. This thing doesn't scale. However, our system becomes bigger, our cognitive load limit stays the same. Yeah. So in the 50s, let's say, they said that our capacity limit for processing information is 7 plus minus 2. Then in early 2000s, another study reduced our cognitive load limit to 4 plus minus 1. So going back to the interrelationships between the four quantities, we can expand the system until we are not able to cope with the resulting complexity. And at that point, we label the system as a big ball of mud. We say that, OK, someday we are going to rewrite it. We are going to implement it from scratch. And this time, of course, we are going to do it the right way, right from the start. Now, paraphrasing Galileo, what happened is the software system has crushed under the weight of its own complexity. So what can we do about it? For that, let's see how other energy supply networks are able to extend their growth limits. And here again, the answer was given almost 400 years ago by Galileo, same guy. In the same book, he said, I have sketched a bone whose natural length has been increased 3 times and whose thickness has been multiplied until, for a corresponding large animal, it would perform the same function which the small bone performs for its small animal. So what he says here is that in order to extend the growth potential, we have to adapt the system's shape. We have to adapt it so it can support the vastly increased stress. Furthermore, he provides another option. He says, if one wishes to maintain in a great giant the same proportion of limb as that found in an ordinary man, he must find a harder and stronger material for making the bones. So to summarize, we have 2 ways of extending a system's growth potential: adapt its form or use more efficient materials. Either way, sustainable growth requires innovation. Something has to change. Let's look at an example of cities. So earlier, I said that one of the factors limiting the growth of a city is overcrowding. But what does it mean, overcrowding? Like, is there a specific number beyond which a city is overcrowded? Well, if you look at historical data, we can see that up until 18th century, the largest cities on Earth didn't actually exceed the population of 1 million citizens. But then, about a century later, something interesting has happened there, and it caused the cities to start to grow exponentially. What happened there? We started innovating like crazy. Look at that. These innovations, they had changed the fundamental rules and opened new growth opportunities. As Eliyahu Goldratt puts it, technology brings benefits if and only if it diminishes a limitation. So in our context, innovation is useful if and only if it allows extending the growth limit of a system, if it diminishes that limitation. So next time a vendor tries to sell you a solution to all your problems, evaluate it from this perspective. Is it going to extend one of your growth limits? So what kind of innovation can we use to extend the growth limit of software systems? Our first option is to find a stronger material. And since the core of our problem is our inability to cope with complexity, if we can find software engineers with superlinearly growing cognitive abilities, problem solved. Someday, probably, there are going to be an AI algorithm that will do that, and it will render all of us useless. But right now, we have to look elsewhere. We need to find another way to cope with this superlinear complexity. And our second option is to evolve the form, the shape of the system, in a way that will help us to manage its complexity. What is the shape? Going back to energy supply networks, Jeffrey West says, highly complex self-sustaining structures, whether cells, organisms, ecosystems, cities, or corporations, require the close integration of enormous numbers of their constituent units that need efficient servicing at all times. This has been accomplished in living systems by evolving fractal-like hierarchical branching network systems. Yeah, finally it's time to talk about fractals. I don't know about you, but when I saw fractals for the first time, I was back in school then, I was fascinated by this elegance, beauty, and simplicity. Now, I was even more fascinated when I was told that fractals are all over nature. You can find them everywhere. You just have to look for them. Well, I looked, and I couldn't find these psychedelic patterns anywhere. And the patterns I found, they were not repeating themselves infinitely like these fractals. So it turns out only the idealized mathematical fractals continue forever. Only mathematical fractals repeat exactly the same pattern at all scales. In nature, fractals behave a bit differently. For example, broccoli is often used as a typical example of fractal geometry in nature. However, you can break it down, I think, like only 4 or 5 times until it loses its self-similarity and reveals the different types of components making it up. So what is popular in nature is not these mathematical fractals, but fractal topology of networks. And they are really everywhere. Here are a few screenshots from Google Earth. These branches of rivers, they're not exactly the same as in mathematical fractals, but they are self-similar in the way the network branches across different scales. And the same fractal topology can be observed in the way energy is delivered in animals, plants, and almost all living organisms. It's also present in human-made systems such as cities, companies, the internet, and others. Here's, for example, you can see an example of fractal topology of roads in a city. Now, doesn't it all sound familiar? Haven't we already talked about all these examples, but in another context? Actually, we have. Remember that some aspects of energy supply networks, they can grow sublinearly, like metabolic rate of different animals, like numbers of gas stations, roads, electrical wires, water pipes. Well, almost in all these cases of sublinear growth, there is an underlying fractal network that actually optimizes the flow of energy and enables these systematic savings. So in our case, in software design, we can exploit this fractal-based optimization strategy to manage complexity of software systems. If we can find a way to use the fractal geometry in the way it is used in other systems, like organisms, ideally, we can turn this complexity function into a sublinear one. Let's see how we can do it. So we said that software design is an energy supply network. The energy it delivers is knowledge, and it flows across boundaries of modules. The way modules are integrated defines the amount of knowledge that is pumped through the system. As in biological and other energy supply networks, the modules are hierarchical. A module can have multiple internal modules and so on. What we need is a self-similarity principle that can be applied at different levels of scale. The same way that branches in rivers that we saw earlier apply the same principle to divide the flow of water. So how can we define it? First, all these fractals in nature, they didn't evolve because the nature wanted some sophisticated, cool-looking designs. No, they evolved because there was a goal. The goal was to be more efficient in delivering energy. So what is the goal in our case? Help me out. Sorry? Delivering knowledge. Yeah, this is what our systems are doing, but we are looking to optimize something. What do we want to optimize by using this fractal? Manage complexity. Manage complexity, yeah. We want to manage complexity through evolving a fractal flow of knowledge. And also, let's take another inspiration from these mathematical fractals. All these fascinating patterns are usually generated by using a rather simple mathematical equation. Let's try to find one for software design. So we said that integrated modules can share different amounts of knowledge across their boundaries. They can expose implementation details, function requirements, models of business domains, or integration contracts reflecting the minimum knowledge needed for integration. Let's call this scale integration strength. The higher the integration strength, the more knowledge is shared across the boundaries. And the more knowledge is shared, the more these modules are going to change together because of the same underlying changes in business requirements or implementation details. Another important property of a connection between two modules is the physical distance between them. And the thing is, the connections between modules, they can span different distances. These different distances are closely related to what we usually call levels of abstraction. Knowledge can be shared across individual methods, classes, modules, submodules, components, microservices, whole systems. And if we continue, we can talk about companies. And the longer the distance between the elements, if these elements have to change together, we'll need more coordination effort to actually implement those changes. In other words, the cost of making a coordinated change is proportional to the distance between the affected components. And now that we have these two quantities describing a relationship between two modules, well, let's analyze some of the possible combinations and how they affect the flow of knowledge across system. So let's start with the combination of low strength over low distance. Sorry, over high distance. Here the distance is high, and thus we have high cost of implementing cascading changes. However, that high cost is balanced by low integration strength. It minimizes the probability of such cascading changes. Thus, this relationship represents what we usually call loose coupling. Now the opposite, high strength over low distance. Here, because of the high integration strength, we have high shared knowledge, and as a result, frequent cascading changes. However, these cascading changes are balanced by low distance. It minimizes the cost of implementing the cascading changes. the interrelated modules are located almost in one place. So it's almost like modifying one component. In other words, this relationship represents what we usually call high cohesion. Now, what about low strength over low distance? Well, here, because of the low distance, the cost of making cascading changes is low, but at the same time, the low integration strength minimizes the knowledge that is shared between the components, and it minimizes the probability of such changes. So what we have here is two unrelated modules located close to each other. And that increases the local complexity of whatever module that hosts them, right? Whoever is going to make a change in that system, well, they have to make sense of what is going on there. It's like, typical example is a monolith. You have many unrelated things, so you have to find the one thing that you actually have to change. So that's local complexity. And finally, high strength over high distance. Here, the shared knowledge is high, so the probability of cascading changes is also high. And to make matters worse, because of the high distance, the cost of implementing such changes is high as well. So what we have here is global complexity. This relationship increases the flow of knowledge across all the system, and it makes it more complex. Now, to reiterate again, these two types of complexities, local complexity is the complexity of a single module, the complexity of its internals. Global complexity is about the interactions happening at a higher level in the overarching module or system that hosts our module. Now, since we're talking about fractals and hierarchical systems, this perspective is subjective. What is considered global complexity on one level is actually a local complexity on a higher level of abstraction. So we have here four options. Where do we want to be? Easy. We want loose coupling or high cohesion. And of course, we want to try to avoid these two complexities. And we can use that preference to say that modularity of a relationship between the two components can be expressed as integration strength XOR distance. Or we can compress it or make it even smaller. Now, this relationship assumes like binary range. Either the strength or distance are low or high. Of course, there are ranges of possible values. But it communicates the idea. We have these two values, strength and distance. We want them to be balanced. We want them to balance each other. We don't want them to have same values, either both being low or both being high. So how can we apply it in day-to-day work? So first, always reduce integration strength to the lowest possible value in your concrete case. We have 4 levels of integration strength, but it's not always possible to be on the lowest one. For example, if two components are implementing closely related business functionality, well, there's nothing you can do here. That's functional coupling. Also, sometimes you do need to use the same model, so there is no point in trying to reduce it to contract coupling. It's model coupling. That's your only option. Once you've got the lowest possible strength, you have to balance the distance. If both strength and distance are high, it will be easier to maintain the relationship between the components if you bring them closer. And if, on the other hand, both are low, you can simplify the design by spreading them apart, by increasing the distance. And finally, make your design fractal. Balance strength and distances at all levels of abstraction. Let's see an example how this model manifests itself in domain-driven design. So say we have 2 proper bounded contexts. So the distance between them is high, but the integration strength, it is low. High distance, low strength. Now we zoom into a bounded context. By definition, a bounded context is a boundary of a model. So the minimum strength increases to model coupling. the distance between the bounded context's internal modules, it decreases. They are located closer to each other than components located in different bounded contexts. Inside of the bounded context, we can find aggregates. Here, the distance decreases further, and the integration strength grows to functional coupling, because an aggregate is a transactional boundary, and its internals are extremely likely to share some functional knowledge. And finally, if we zoom into the methods of one of the aggregates, here the distance is minimized, and the strength increases to implementation, as code on this level probably assumes some knowledge of implementation details. Now, this was rather coarse-grained example. We started from a very high level, multiple bounded context, and used that as a starting point for comparing distances. However, this approach, it can be applied if we shift the perspective to one of the internal modules and use it as a starting point, use it as a reference for the maximum possible distance between the components. We can use the same reasoning to organize how its internal components work and how they are integrated. Again, this time at a finer grained scale. And it's possible because these levels of integration strength, they are not absolute, they are relative. What's considered an integration contract on one level of abstraction, it will be an implementation detail on a higher one. It's exactly the same idea as the local and global complexities are also subjective. What's considered global complexity on a lower level is local complexity on a higher level. So this is our fractal geometry. This is the self-similarity. If it's observed at different levels of abstraction, it is going to optimize the flow of knowledge and manage the complexity of the system through encapsulation of that knowledge, only exposing the knowledge that has to be shared. To sum it up, as Rebecca Wiersbrock says here, the most effective tool for dealing with complexity is abstraction. Many types of abstraction can be used, but encapsulation is the main form of abstraction by which complexity is managed. And we can use this simple relationship between integration strength and distance to increase encapsulation through a fractal-like network of knowledge sharing. And it's time to wrap it all up. So what we saw here, what we did is we recognized that software design is an energy supply system. As such, it follows the same underlying laws and principles as living organisms, cities, social structures, and other energy delivery systems. To exploit this model, we had to identify the energy that is delivered by software design, knowledge. We used it to identify the different dynamics of scale that are limiting software systems' growth potential. And to extend the possible growth, we took a page from other energy delivery networks and used the common energy optimization strategy, fractal geometry. To apply fractal geometry to software design, we identified the simple self-similarity principle that applies at all scales. Integration strength, XOR distance. If all this stuff sounds interesting, I wholeheartedly recommend reading the book, the original book, Scale. And if you will read it, you will see that I cut some corners when defining software design as an energy supply system because, well, I don't have time. But you will see other requirements, such as invariant terminal units, that systems have to be space-filling and that have to be optimizable. That will be your homework. Think about how software design answers these requirements, and it does. If you're interested in more quantitative research about this topic, look for papers on power laws and scale-free networks applied in software. Basically, this is a different model for talking about the same things. Here are these papers analyze software from the fractal geometry perspective, looking to measure the encapsulation of knowledge and at different levels, ultimately coming to the conclusion that, yeah, if there is no fractal geometry, we get a big ball of mud, but well-designed systems do follow this geometry. And the final book I can recommend to check out is this one. Unfortunately, I have no idea when it's going to come out. I can write a whole other book. It's going to be a thriller about all the things that went wrong during this writing process. I hope it's going to be early next year. I'm trying to talk the publisher into releasing a rough cuts version, meaning that we'll release my draft manuscript without any copywriting or proofreading, so it's going to be not for the faint-hearted. But what you can find in the book is, of course, a more detailed story of what I showed you here. So first of all, you will see how this integration strength relates to models such as structure design, kinescence, where it came from, why I prefer to use this one instead of other modules. You will see a different way, a more detailed way how to evaluate integration strength so that you can compare it to two relationships of the same type, for example, two model-coupled relationships, using some additional degrees between them. And yeah, I would love it to be published on due date a year ago, but we software engineers are bad with estimates, so don't blame me. Part of the job. And with that, I have to say thank you.